Okay, so this will be the solution for question 6 on exam 1, Physics 116 exam 1 from winter 21. And this particular question is looking at concepts of period of a block attached to a spring. So that's sort of given by this expression down here. So the period of a block attached to a spring is given as a product of 2 pi times the square root of the mass of the block divided by the spring constant k of the spring. We'll also need to sort of be comfortable with position versus time graphs of a simple harmonic oscillator and how to denote period information from that particular graph. So this is coming from sections 14.3 and 14.4. So that's from chapter 14 in College Physics, Knight, Jones and Field. So let's jump into the question. So we've got a Physics 116 student. It forms two simple harmonic oscillators. For each oscillator, a block is attached to an ideal spring. Springs in both oscillators are identical, so that's what we mean. We now know. We can maybe start with that. I can say that Ka equals Kb, so they're identical springs. But in the oscillator A, a block of mass Ma is attached to the spring, and in oscillator B, a block of mass Mb is attached to the spring. So where the masses of the blocks are different. And then we're given a graph of the position versus time. So that's what sort of had mentioned the concepts. I've been able to denote period information from that graph. So we can see here that they do have different periods, and the relationship. We're trying to determine the relationship between the mass of the blocks, and that will be denoted from a difference in the relationship of the periods. So what we can see here, let's start with oscillator A. So we can see the oscillator A starts from 2 meters and moves down to -2 meters in 4 seconds. So that's only half of a period, half of the period. It has to come back to its original position in order for it to complete a full cycle. So if it takes 4 seconds to get from max to min, it'll take another 4 seconds to go from min back to max. So we can see that the period of A is going to be 8 seconds. Now for B goes from 1 meter to -1 meter back to 1 meter. So oscillator B completes one full cycle after in 4 seconds. So the period of B is 4 seconds. So what we can see here is that TA is equal to 2 TB. So that's sort of relationship. So the relationship between the periods will allow us to determine the relationship between the mass of the blocks. So we can write the period of A as 2 pi the square root of Ma over Ka, which is equal to 2 times, actually we'll keep the parenthesis there, 2 pi square root of Mb over Kb. Now we can make some cancellations, so we can definitely cancel out the 2 pi's on both sides. We can also cancel out the Ka and Kp's because it's just K, it's just same spring. So we're going to end up simplifying this expression to the root of Ma equals 2 times the root of Mb. Square both sides to get rid of the square roots. So Ma equals 4Mb, and that's the correct answer for this particular version. In the second version, I reversed the oscillators, that TB was 8 seconds and TA was 4 seconds. So once you sort of set up the correct relationship, so in that case, the TA would only be half of TB. So you'd end up getting TA equal to sort of down here. You'd end up with maybe I'll try to write this down. Sort of for the second version, you'd end up with the root of Ma equals the root of Mb divided by 2. So for the second version, where I sort of reverse the oscillators, you'd end up with Mb over 4. But that's just for a second. For this version though, so it was one version was Ma was 4Mb, the other version with Ma was 1/4 of Mb. Again, if you were to make the sort of inverse. Okay, yeah, I'll wrap up the question there and follow up with question 7.